Welcome to the Hyperbolic Coding Chamber. This is day 49 of daily LeetCode, daily LeetCode, day 49. Yeah, it was a good session yesterday. I was just reading the comments, and you're gonna make sure to join the Hyperbolic Coding Chamber. This is actually true. Actually true. Special guest appearances every night, such as Drake, Bill Gates, and many more. Thousands of members from all around the world are joining every single day. This is actually facts. We have a committee. It's me, Copy Ninja, and I'm just that guy. We're talking. We talk with Discord. We're using so much bandwidth on their servers. We're thinking, we're in deep talks with them. We're like, we need a way to get in contact. We need more resources, basically. So right now, their Discord is asking us to pay them, right? Because we actually have so many members in the Discord that we're actually using up more than half of the Discord's resources. So we actually have to pay them. And so you're gonna want to tune in tonight because the the CEO of Discord, is actually going to be in the Discord tonight. Actually true. He's gonna be in the Discord tonight, and he's gonna be giving out all the cheat codes. All the cheat codes for the servers. He's going to be letting everyone know basically everything you need to know about Discord, and we're going to have a live open discussion about the server resources, and it's going to be a bidding war. It's going to be crazy. But yeah, just a W comment. It's just actually true. It's actually true. And yeah, so I think next week, we're going to talk with Drake. We're going to talk with Drake, Chance the Rapper. Any of the hottest musicians right now, Adele. We're also going to have probably, you could name anyone. We have a long roster set up, so you're going to want to tune in next Friday into the Hyperbolic Coding Chamber because Drake is going to be doing a live concert. So yeah, you're going to want to tune in. W comment, W experiences, and let's have Thomas Wong. Love your video. Gotta keep grinding. Facts. I'm gonna say thank you, brother. We will. You and I. Much love. W human. But yeah, this comment is so funny to me. I don't know why it's so funny. But this is actually true. This is actually true, actually happening. That being said, you're gonna want to tune in. Make sure to join the Discord. But reflections on yesterday's grind. We had a problem we were doing called threesome, and I think we actually spent almost an hour debugging this, and this is actually crazy because we were debugging this, and then I realized, I was just having so much trouble debugging this. I started deleting lines of code, basically because the code that we were failing on, the test case, was a very, very long test case. It had just an inordinate amount of strings or numbers within it, so it actually made it harder to find the problem because I just couldn't understand why this wasn't working. Now it took me an extra 35 minutes to figure it out. It was this line right here, nums.sort. So this is actually crazy. If you go into a REPL, a JavaScript REPL, right, and you do nums.sort, it's going to sort the numbers as strings. So sort without a comparator sorts the numbers as strings. The part that's doubly confusing, right, for a small enough sample size of numbers, sorting them by strings is actually going to be the same order as if they were sorted as if they were numbers. And so the cases that we were failing on were these massive numbers. When we would sort them lexicographically, like as a string, the order would be messed up. And then, it took me forever to figure this out. But I'll never forget it. Now I know, right? Default sort mechanism is by string, right? And then you need a comparator, right, to make that happen. So we're never going to forget that, which I guess is part of the whole thing, part of the learning journey, part of the, just trying to get better at something. So it is what it is. It was kind of cool to find out. It was kind of cool to figure it out in the moment when it was cool to finally figure it out, but on the way to figuring it out, I'm going to be honest, it was torture. It was torture figuring it out. It just was. So that is tough. And so we have some new problems to do today. right? The new problem to do today is coin change. It's not really new, it's just a review problem. But we have actually a lot to review. So I said lots of review to do on our path to becoming a one-piece admiral. So I would say right now we're like episode, I would say right now we're like episode 35 Luffy, maybe episode 60 Luffy before he even goes gear first. That's where we're at right now. Generally, if we run into a problem that's not very technical, it will be solved. But if you run into anyone who has a devil fruit, I mean, you're finished, right? Like Luffy was finished. So still leveling up. Want to do this problem coin change, but historically this is a problem that we have failed many times. It's been a brutal beatdown when we do manage to solve this problem. It's a brutal beatdown. The time complexity is like, when we do solve it, it runs and it says like it took like 30 seconds. In the space, it took like 5 gigabytes of memory. So this is just not going to work. So hopefully when we solve it this time, it'll actually be closer to an algorithm that is palatable. That would be the goal, right? So that, and then we'll see what other problems remain. Right? If we can get through coin change, which I honestly doubt, but we shall see. It may be possible. But yeah, I mean, we also released another, the last video yesterday was called Fry Time 4. The beginning is the end. And I don't think today is going to be a movie. I think it's going to be a beatdown. So I'm going to call this, I think I'm going to call day 49, or I'm going to dub it as coin change beatdown. And hopefully I'm speaking it into existence. Hopefully we're going to beat down coin change. But as always, you're going to want to make sure to join the Hyperbolic coding chamber. Thousands of people joining every day. I mean, at this point, if you click the link, you might not even get in. Honestly, if you click the link, you might not even get in. So, yeah, there's thousands of people joining every day. We're gonna have the CEO of Discord is gonna speak tonight in the Discord. So you're gonna want to make sure to join. And yeah, we're just gonna jump into coin change. We're just gonna jump into coin change, and then yeah, we'll see how far we get. But make sure to join the Discord. Let me know if you're doing something similar. Let me know if you're grinding. Let me know if the video is the worst video you've ever seen. Let me know if it's semi cool. Let me know if yeah, let me know what's on your mind. Let me know what you had for dinner. Let me know what's on your mind. And yeah, we're just gonna jump into it. Coin change problem. So let's jump into it. Gotta slow down. I actually have to load up a program first. So here we're back again. We'll say this is the review notes from the last time we did this problem. Don't just run the code. So I think last time we did this problem, we went with a method that I think created exponential time. And I think we just started guessing. So I think I wrote if you get overwhelmed by following the recursive tree, use a smaller example, which is good advice. Also, the current approach is ridiculously slow, which is also true. And I also said no, try a BFS approach. Well, I don't know if we'll follow a BFS approach. I think we can. I think there might be a better way to solve it. Maybe we can think through it, maybe we can get through it, and maybe we can intuit some dynamic programming intuitions. But yeah, you are given an integer array of coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of coins, return -1. You may assume that you have an infinite number of each kind of coin. So you're given an integer array of coins representing coins of different denominations. Let's map this to our example. You have an integer array of coins representing coins of different denominations and an integer amount representing a total amount of money, which is 11. You want to return the fewest number of coins that you need to make up that amount. And it looks like the fewest number of coins is actually 3. It'd be 5 plus 5 plus 1, which gets us the amount 11 and the output 3. Now when coins is equal to 2, right, there's actually no way for us to get to 3, so we return -1. That's a good point, right? We can see that when our coin is 1 and our amount is 0, right, then we can always use no coins, right? So if we use no coins, then we can always get an amount of 0. So one thing we can code ahead of time, we can just say if amount equals 0, then we can just return 0, right, because we can just use no coins. So if you look at our coin lengths, we know that our coins.length can be up from 1 coin up to 12, so we'll always have at least 1 coin. Coins values go from at least 1 up to 2 to the 31 minus 1. So that is pretty cool. And we also have amount, which can be less than amount, which is going to be 0 or up to 10 to the 4. So that is interesting. So interesting. I think just to generate some naive methods to how we could solve this, I think what we could do is view this problem as a graph, right? And maybe up to n graphs, because we have each coin, right? 1, 2, and 5. We want to know how many different ways we can get to 11, the amount, but mostly the shortest path there. So what we want is actually, we visualize problem as graph, then we can rephrase the problem as finding the shortest path, which is interesting. I think if we rephrase the problem, we can look at it as finding the shortest path to 11. Which it gives me another idea that if we knew the Dijkstra's algorithm, we could probably solve it that way as well, because we could view it as finding the shortest path to this node 11. But I think Dijkstra's is for a unique path, but honestly, I don't remember too well. Either way, we're not really certain how to implement that algorithm, so it might not be something we're capable of doing. So we visualize the problem as a graph, and we can rephrase it as finding the shortest path. Now, if we want to find the shortest path, maybe the best way we can go about that is with a depth first search. If we do a depth first search, then we're going to know that at minimum we're going to have coins trees. Right, we know we're going to have coins trees because, right, you can either start at 1, you can start at 2, or you can start at 5 for these particular amounts. And it's possible, right, that the shortest path starting at each of these different amounts is a different path, right? For example, you can get a path of 3 from 1, right, by going, we can create these 3 paths here, right? You can take 1 to give you a path which would give you a sum of 2, right? You can take 2, which will give you a sum of 3, and here, which will give you a sum of 5. And then if you go I mean, if you have a sum of 6, if you go to 5 again, you actually end up with a sum of 11, right? Which is also the same path that's reachable from this node all the way over here, right? So we could take 5 to end up at 10. Then we could take another 5 to end up at, 1. Now, if we do that, we'd end up at 11 total, which is still the shortest path, which is 3. The only one for this is different is actually 2, where I think the shortest path would probably be 2 plus 5, which would give us 7, and then 2 more, which would give us 9, and 2 more, which would give us 11, which would actually be a total path of 4. So 2 plus 5 plus 2 plus 2 is a path length of 4. Now, I think what we're going to want to do, though, is memorize our solution somehow. But I think what we can do to start is pretty much generate all paths, right? We could generate all paths. If we could generate all paths to our goal amount, which would be amount, right? And then we'll just take the minimum of all the paths and have it. It should recurse back to the top and give us the minimum amount, right? And I think we can see additionally with this example that there's room to memorize our solution because, right, even here we'll be visiting 5, 5, and 1, but we know that once we reach 5 in this point, right, 5, 5, and then you get to 11, right, we'll actually be recalculating a lot of values that I think we could save. For example, if we take a path here too, right, we could take a path of 2, right, and then take a path of 1. Excuse me for the gas. We take a path of 1, we end up at a sum total of 5. This sum total of 5 would actually be the same 5 right here. We know that from this 5, it takes two more edges to get to 11, right? So we know that our total path here would be 1, 2, right? 1 it would just be 1, right? Plus the path, the number of steps you are away from 11, which is actually 1, 2, right? So it'd actually be how many denominations? Well, 2 plus 2 plus 1. Oh no, right. So it actually. All right. I'm using the nodes here, but we're actually trying to denote the value. So we go from 2 to 2, right? Our value is actually 4. We can get to 5. Our value is actually 5. Now to go from 5, right, to 11, you can do 1, 5, and then 1, 1, which gives you 2. When you get to amount 5, right, there's actually 2 more steps you can take to get to 11. So if that's the case, if there's 2 more steps to get to 11, and it takes 2 steps to get to 5, the total path to get from 2 to 11 is actually a path length of 4. So we're going to need a way to take the minimum of those values going forward. That being said, we're going to need to do DFS starting at each coin with each coin. With each coin having with each coin equaling a particular starting value, and then we're going to want to return the minimum of that as our answer, right? The minimum number of denominations, right? But we're also going to start min at infinity, right? If we start min at infinity, right, if none of these can actually reach our goal amount, then they're also going to return infinity, right? And then we can do if min equals infinity, right, then it means we actually have no valid paths to our amount. Now, if that's the case, we'd like to return -1. Otherwise, we'd like to return min. And then, right, let's try and implement this. So I think right now, if we were to implement this, this would actually be S, right? So we have, let's just say we have, let's just call the number of coins C, right? And we'd actually do C to the C operations to visit all paths between every possible path this graph could create, right? Because for every coin, right, we have up to 3 potential options, and this grows exponentially as we get until we pass amount. So if that's the case, then we're going to want to iterate over coins. So for const coin of coins, we're going to say min is equal to the math.min of min, or the depth first search, right, given all coins, right, starting at a particular, so we're going to have to pretty much prototype the parameters we're going to need for this function. We want to do a depth first search that visits all coins. We're going to need access to all the coins. We're going to need access to all the coins. It's going to be an array of numbers. We're going to need access to our value, which is going to be a number. It's the value we start at. We know the value we start at is going to be equivalent to the coin's value for our number of trees. So if we have 3 denominations, we have 3 potential trees to search for the minimum path to our amount for. So I have coin, and we need, I think, a way to keep track of the length of the path, right? And so this could start at the length of the path actually starting at 1, right? Because the initial denomination could count as a node. Now, is that all we need? The coins, the coin, and the path so far. So you call this path length, which would be a number, right? And this function is going to return a number. This function, right, for each depth first search, right, it's going to return, right, the shortest path to amount, right? And so we're also going to need access to amount, and we can't forget that. Make this a little bit bigger. We're going to need access to amount, and so we'll add amount as a parameter to the function. And so we want to return the shortest path to amount, right? Well, we know that our path length is a particular number, right? So we're going to have a couple of cases, right? If our value, right? So the goal here is, right, is to code the base case and hope that it propagates up to give us what we're looking for, right? So we'll solve for the simplest case and have recursion do the rest of the work to make an answer that makes sense. Oh, I'm very gassy today. We have value, right? If our value is greater than amount, right? So if our current value is ever greater than amount, then it's not a valid path, right? We can imagine this for our coins. Let's say our goal amount is 2. If we start with a value of 5, or if we ever get to a value greater than 5, then what we found is that this coin, or the current path we took, right, which is just starting at 5, is not a valid path to amount. In those cases, right, we'd like to return infinity because it's not a valid path, right? This would also help us down here, right, where if something's not a valid path, then we just have to choose between the minimum of infinity and infinity, or the smallest value so far and infinity. And if there's no path, we should have infinity. right? But else if, right, value equals amount, right, then it means we did a good thing. We found a way to get to this path, right? And so we can check, let's say our amount was equal to 1, and we start at coin equals 1. So at coin equals 1, right, we'd have our coins array, our amount would equal 1, our value is equal to 1, right, and our path length would equal 1 to start. And then we'd say, hey, 1 does equal 1, so our path would actually be, we just return the path length so far, right? But we actually started with 1 here, so we could also do something else where we return path length plus 1. The trade-offs for this are going to depend, but it seems like in this base case here, returning path length seems to be fine. But I think when we recurse deeper, we're going to want to do path length plus 1. Now, if we make it all the way out here, what we know for certain, right, is that value is currently less than amount, which is a good place to be in, right? Because now we want to search even further again. So we're going to create a new min, which is equal to infinity. We're going to want to iterate over our coins again, const coin of coins, and we're going to say min is equal to the math.min of min, which is infinity, right? And amount, which is always going to stay the same, right? And value, right? But our value is actually going to depend, right? Our value is going to depend on our next path and our next node that we visit, right? And that is actually going to be value plus coin. So if we start at 1, right, and our goal amount is 2, right? Value is not, 1 is not greater than 2, and 1 does not equal 2, right? So we want to find the path to 2. We're not there yet, so we'll do math.min of infinity, or we actually messed up this call. We're going to want to do DFS like this, right, of amount of coins, amount, and value plus coin. And the first coin is actually going to be 1. Right? So our value is going to be 1. Our first coin is also going to be 1. So we're going to add 1 and then do path length plus 1. Right? And if we do this, right, if we had 2 coin denominations, right, and our goal was 3, so let's imagine this. We'll have C equals 1, 2, right, and M equals 3. We'll visit M equals 2, right? We'll start down here. We'll say for const coin of coins. So we're going to want to run a DFS starting at each coin's base amount, right? We're going to have 2 trees, 1 and 2, right? The value we're going to start with is going to be coin, right? Coin is not equal to, right? So we have 2 paths to go from 1 and 2, right? We can go 1, or we can take a path of 2, or we want to take the minimum path of choosing both of those options. So we do min of DFS coins value plus 1, and our path length plus 1. That's actually a path length of 2, right? And if we go to our next iteration of calling this DFS, it'd be infinity versus 2, right? Because once it equals the value, we just return it and it doesn't propagate any deeper. We'd come back in here, we'd still be right at C equals 1. Then we're going to add 2 to it, right? And if we do value, which is 1 plus 2, which equals 3, if it equals 3, right, then like we said, 3 would be greater than amount, we'd return infinity. Now the minimum of infinity, infinity, and 2 is 2, so the shortest path we would return would actually be 2. But what's most important is that we're taking this running min. So this would eventually return infinity. What's the smaller, infinity or 2? Well, 2 is smaller. Then we want to try finding the shortest path, right, when we go to 2, right? And if we do that, we'll say min DFS of coins amount a path of 1, path length of 1, right? When we pass 2 and 2 is already equal to amount, so we just return path length, which would be 1. So I think this does make sense to start, and we want to make certain, right, to handle what we said earlier, where if amount equals 0, right, then we know that we can just use no coins to create that. So I'll comment this out, and I think this makes sense to start. We can check if our DFS calls make sense. We have 4 parameters, 1 coins, amount, number, value, path length, and 4 parameters are used there. 4 parameters are used here, and let's try running this for our first example. So we do get the first value correct. Now let's try a different example with a denomination of their second example, denomination of 2 and amount of 3. So we seem to be good there. Let's try a new version. We take a denomination of 1, right? All of our denominations are 1, and we do amount equals 0. So we're good on these test cases to start, and I can't really think of any other test cases to try. Let's try one where the amount is 1, right? And our best path we should be able to do should be 1. So let's try and see. I think this is definitely going to be time limit exceeded because this is exponential time basically for a large enough input size. Right, so time limit exceeded. This is exponential time and exponential space as well, since we could be recursing pretty deeply into the stack, into the call stack. So I think maybe there's a novel way to optimize this, and the novel way to optimize this could be there could be a novel way to optimize this. I wonder if well, when we go, oof, my insides hurt. When we go past amount, right? Once we go past amount, once we go past amount, once we go past amount, we tend to stop, right? So I'm wondering, right, if we already know our current minimum value, right, maybe we could optimize this by not going any further. But I think we'd have to know how much our trees are playing into this problem before we use it as a vector for optimization, right? So if we know, right, that our shortest path so far based on our first traversal, the best we've ever done is 3, right? Then if we're visiting another coin or another tree or going down a path length, and our path length is already greater than our shortest path length, then maybe we can just stop. That way we'd only ever visit the trees that have a potential, or we only visit trees up to a potential that they have to shorten our path. So if that's the case, there's also another way we could memorize this. So to try this optimization, maybe we need to keep track of our our shortest path so far at all times. We'd need to know our shortest possible path at all times, and that could get sticky. Oof, that could get sticky. So if we know that we can, what if we kept track of our shortest path at all times, then we could pass this into DFS. In this case, we'd pass in our minimum, right, which is infinity, right? But on our next tree, we'd know our shortest path so far, and we don't want to visit any nodes that could be greater than that. Right, and I'm thinking we could do if path length is greater than shortest path so far, I don't think, or if path length is greater than our shortest path so far, then I don't think we definitely don't want to continue. We'd want to return infinity. So if we tried for a smaller tree, right, like what we had earlier, let's try and recreate a novel example. We had a path of 1, right, and we also have a coin 2, right, and let's say our goal denomination is 1, right, amount equals 1. In our current example, even if we reach 1, right, we still have to build the entire tree for 2. While this is a small example, the tree will not necessarily be large. It could be quite large depending on the number of denominations. So I think what we definitely want to do, if we visit 1, right, our shortest path so far, right, if we pass in min, it's going to be infinity, right, and our path length so far is going to be 1. 1 is not greater than infinity, right? So 1 is not greater than infinity, right? Since 1 is not greater than infinity, we would never do anything. So we want to be able to use this somewhere that will shorten our paths. We'd only know in this first example, right, where we return path length. So now I think I'm noticing that the best we can do is limit this from a tree-to-tree basis, right? If we take our shortest path length so far, all we can do is really pass it. All we can really do is pass it back in, but we'll calculate a value, right, which is min, right? It's going to be our shortest path so far, right? Nothing's going to be greater than infinity, so we'll be fine. Then we return it, we'll return a path length of 1. When we go to visit 2, right, we'll say if path length is greater than, if path length, right, is greater than or equal, if path length is greater than or equal to shortest path so far, right, then maybe we want to return infinity, basically. So I think what we want to do is add shortest path length, which would be a number, and we'll say else if path length is greater than or equal to shortest path length, right, then we want to return infinity. And I think we could actually fuse these cases up here together, and then we'll want to pass shortest path length into min here, right, into this call of DFS to avoid wasting time in this function as well. And then we'll pass in, we're already passing in min here, so we'll be using it here. So I think this makes sense. Oops, and I forgot to comment out these. So we still get our answer here, but I think in this, in the case of 1, 2, and 5, and 11, this should be faster because we shouldn't have to visit 2 or 5. It's hard to know if that was faster since we didn't really keep our previous amount in. Right, so it looks like this is still not good enough of an optimization, which in retrospect makes sense because we still have to visit pretty deeply. It pretty much just cuts the search basically, which means you still end up creating quite a large tree. It's just that if it's shorter than the shortest path so far, then we'll stop. So I think our next best approach would be to memoize this, right? We could use a a map to save the amounts that the shortest paths for amounts that we've already calculated. So let's say, right, we have a couple of trees here, right? We'll use this example right here. Amount is equal to, let's do something small, like 3, right? And our denominations are going to be 1 and 2, right? We know that if you go from 1 to 1, right, the next thing we're going to visit is 1. If we know the next node we're going to visit is 1, then we know that once we pretty much finish visiting this node, right, that the shortest path from from 1 to 3, right, we'll already have calculated that. What we really want is these intermediary values to be saved, right? So if we go to 2, right, we know the shortest path from 2 to 3 is going to be taking 1, right? And so that way, once we visit 2 here, we don't have to recalculate it, right? And even once we visit this one right here, we know that 2, right, which starts at the path length of 1, right, we know that the shortest path from here is 1, right, to 3. So we can just, since we don't actually have to print the path, we'll just know the length. So this map that we're looking to use to memo-wise is trying to store for a particular value, right? It's going to map it to minimum path to amount, right? That way, once we calculate it, if we're at a particular amount, we've never seen it before, right, we can set it to a new value. And so this memoization part is where it gets a little funky. So we can replace this last parameter. Instead of shortest path, we'll have memo, and it's going to be a map of number to number, right? And we'll remove references to shortest path length. And we'll remove this extra comma because now we're looking to memoize this. So since we're looking to memoize this, where would be the best spot to save it, right? So we only know the minimum path for a particular value, right, at the end of this for loop, right, is the only time we really know for certain, right, because we have to take the minimum path length for traversing each subtree, which can start at any coin, right? We only know that value here. So maybe, right, we can set this value, but I think it's not that simple, because if we set this value, it's going to be not the distance, but so if we start at, so let's track this through. We start at coin 1, right, and we can either take 1 or 2, right, and our goal is to get to 2. The shortest path, right, in the end, starting at tree 1, is going to be to take one more coin of 1, right, to get to 2. But our path length is already 1, so when we get this map here, the min that we actually return is going to be 2, right, 2, and then infinities, right, since if we go from 1, right, and we take a coin of 2, we'll get to 3, which will return infinity. So I have to choose between 1 and infinity. 2 and infinity, but it's actually not what we want, because this actually shows the entire length of the path, which should actually give us uniform values. We want is the number of steps from 1 that you take to get to amount, that way this value can be reused. So if we change amount, let's just say we change, we have these coins, right? 1 and 2, right? And our goal amount is 4, right? We want is new, so if we go 1, right, it's depth first search, we're actually going to get to 4 first by doing 1 plus 1 plus 1 plus 1. That path is of length 4, right? We're going to know that path, right, once we join in here, right, with the values equal to 1. We're going to know that that path is going to be, we're going to either choose between that and a few other paths, right? But the shortest path is going to be 1, 2, 1, right, which is a total path of 3. But throughout those values, what we want to save is to say like, hey, 2 is actually minimum 1 step away from the value by going another 2, right? And 3 is actually 1 step away from amount, right? So that if we ever end up having to recalculate this amount, for example, right, we could take an amount of 1, right, or an amount of 2, right? What we can do is just say, hey, does our current value, which is 3, already exist in the map? Well, it does. So what we can do is just add our current path length, which is going to be a path length of 1, right, plus the path length, the minimum path length to get to amount from 3, right? That would actually be 2, right, plus 1 gives us a total path length. 1, right, plus 1 would give us a total path length of 2. Basically what I'm saying is we want to be careful the value we set to, what we set value here to. Because that total, if we set it equal to path length, we're just going to get the total path length, and that's not what we want, because that's going to be specific to the path it took us to get here. We want is to know, oh, from this amount 3, right, it takes us 1 step to get to 4, not that we want to set 3 equal to a path of 3, right, or 2, because that's what we would do. If we set map.set value, right, and we did min, that's actually what we would be doing. We'd be setting it to 2. What we want to do is set it to the math.absolute value of min minus path length, because our path length would be 1. And then the other thing we can do is say, we'll change this to an else if, right, and we'll say if, and we actually use map down there, we want to use memo. I'm going to say if memo dot has value, right, then what we actually want to return is going to be, we want to return the path length so far plus the distance, right, the shortest distance from this current value to get to amount would be map.get value. And if we run this again, we kept saying map and it's supposed to be memo. This is also missing memo as a call. If we go to line 34, we have an arbitrary const just sitting there. And we forgot to add memo here as well. Right, we never created memo. It'd be a new, wait, I think we did up here. Oh no, we didn't. Create a new array, a new map, right? It's gonna map numbers to numbers. Oh, so right. So this is, So this version is still pretty slow. It's 441 milliseconds. So it's still pretty slow, and I think that partially has to do with starting at, it doesn't use all the optimizations it could. I think we could also do if memo.has a value for coin, right? Then we can just say memo has a value for coin. Memo has a value for coin. And we can just check in the map, right? We can say memo.getCoin, which will give us the shortest path for this coin, right? And we can do the same thing we did earlier. We'll set min equal to the math.min of min, and memo.getCoin. I think we're going to want to add, are we going to want to add 1 to it? I think we don't need to. And then the else case, where we call it depth first search, can exist here. So we had 441 before. Let's see what we get now. So we actually get, oh, so okay, maybe you do still have to add 1 to it, right? Because it's going to get right. Okay, so I think you still have to add 1 to it. So this is faster. This is 315. And I think we could actually optimize this whole thing if we copied this loop right here and we put it here instead. And then replace this math.min with this one. Replace coin here with value plus coin, and then say math.min of memo.get. Right, we don't need to add 1 here because we already have the path. We'll do path. Our current path length so far. This would be our current path length so far plus the value of getting the value in the map of value plus coin. And it looks like we still have to add 1 because we do path length plus 1 to enter value plus coin. This is a little bit faster. It's not that much faster. Yeah, I think this is time complexity here. So I think it was, if C is the number of coins, right? For each coin we can visit up to C. Oh, no. If C, all right, if S is the number of coins, then we can visit up to S neighbors from there. So I would say it's S to the S or N to the N. Because for every neighbor we can visit, for every coin we can visit up to C, we can create up to C neighbors or C paths. So let's say it's C to the C, which is pretty close to exponential time. So it's exponential space, but since we're using a map to memoize this, I think it would be using a map to memoize this, which means that if we're trying to calculate up to a denomination n, then we actually only visit all the values up to n if we've already calculated it. But it's not all the value. It should be all the values up to n that are supported or that you can reach by adding these denominations together. I want to say at the minimum it's exponential time, but it's hard to tell where the map aspect plays in here. The problem can be modeled as the following optimization problem. The minimum of the summation of I starts at 0 going to n minus 1 of x of I, subject to I, the summation of I going to 0 to n minus 1 of x I times ci equals s. S is the amount and ci is the denominations. Ci is the coin denominations, xi is the number of coins with denominations, ci used in change of amount of s. We easily see that x is equal to 0 comma s over c sub I. A trivial solution is to enumerate all subsets of coin frequencies x over to xn minus 1 that satisfy the constraints above, compute their sums, and return the minimum among them. To apply this idea, the algorithm uses backtracking technique to generate all combinations of coin frequencies in the range 0, comma s over c sub I, which satisfy the constraints above, makes a sum of the combinations and returns their minimum, or -1 in case there's no acceptable combination. So coin change, they return coin change for a particular coin index, the array of coins, and the amount. So if amount equals 0, they return 0. Otherwise, if IDX coin is less than coins at length, so it's a valid coin, and amount is greater than 0, our maximum value is amount divided by coins sub IDX coin. And the min cost then we do from int x equals 0 to x is less than max val, amount sub could we improve the exponential solution above? Definitely, the problem could be solved with polynomial time using dynamic programming technique. First, let's define f of s, the minimum number of coins needed to make change for amount s using coin denominations c0 to cn minus 1. We note that this problem has an optimal substructure property, which is the key piece in solving any dynamic programming problems. In other words, the optimal solution can be constructed from optimal solutions of its subproblems. How to split the problem into subproblems? Let's assume that we know f of s for some change, val sub 1, val sub 2 for s, which is optimal, and the last coin's denomination is c. And the following equation should be true because of optimal substructure of the problem. F of s is equal to f of s minus c plus 1. In other words, the optimal solution can be constructed from optimal solutions of its subproblems. How to split the problem into subproblems? Let's assume that we know f of s for some change val for s, which is optimal, and the last coin's denomination is c. And the following equation should be true because of the optimal substructure of the problem. F of s minus c plus 1. But we don't know which is the denomination of the last coin. We compute f of s minus ci for each possible denomination. We choose the minimum among them. Following recurrence relation holds. Recursive tree for finding coin change of amount 6 with coin denominations 1, 2, and 3. Interesting. Yeah, this one is interesting. This one is interesting. Don't. Okay. Yeah, I don't really know how to make this one better. Don't really understand dynamic programming. We need to read more about that. But the approach we're currently using is quite slow. It barely passes. It's also hard to tell the time complexity. We are caching the solutions though. Wait, I think this is my solution. $530. I'm pretty sure this is my solution right here at the 537 mark. Yeah, I'm pretty sure that's my solution. I think I can tell because if I go back here, yeah, 547. 547, I think they said. That is really funny. So basically I'm at the top. Oh no, 537. So right here, basically I'm at the top of the bracket basically. So my solution is kind of the top solution. It's kind of the top worst solution, which is kind of interesting. Read more on dynamic programming. Job on using trees to explain approach. What were some other things? Clearly backtracking are some ideas on how to test time complexity on. This one is a tough one. But we'll just go to the next one. So just delete that code really fast. So we want to be able to figure this out. The last note for this one was try to intuit a depth first search of n plus n. Try to intuit the DFS O of n plus m solution. So given a reference of a node in a connected undirected graph, connected meaning that since the nodes are undirected, connected in the sense is going to mean that you can reach any node from any node. Return a deep copy or clone of the graph. Each node in the graph contains a value int and a list node of its neighbors. We have class node, public int val, and public list node neighbors. For simplicity, each node's value is the same as the node's index. One index, for example, the first node with value equals 1, second node with value equals 2, and so on. The graph is represented in the test case using an adjacency list. Adjacency list is a collection of unordered lists used to represent a finite graph. A finite graph. Each list describes a set of neighbors of a node in the graph. Given node will always be the first node with value equals 1. Must return the copy of the given node as a reference to the cloned graph. Pretty much we'd have to clone this graph. You can see that we have some examples here. This is the original graph. This looks like a clone. The nodes are new. The graph looks the same. Right, this looks right. We go up, you can't return the same graph, which makes sense. It's not exactly a clone. The nodes were cloned, but the graph is messed up, right? We want to retain connections. We have example 2 here, right? And so we have an empty, a node has no neighbors. The input contains one empty list. The graph consists of only one node with val equals 1, and it does not have any neighbors, which makes sense. Adjacency list is empty, then our cloned graph is also empty. So before we ask any clarifying questions, we will know that if the node doesn't exist, we can return an empty array. Right, now if the number of nodes is in the range 0 to 100, so we're handling that already, since the nodes can't exist, we'll return an empty array. The node values are between 1 and 100, and node data value is unique for each node, which is good, which means we can use the value as an ID. There are no repeated edges and no self loops in the graph. So no repeated edges, which is good, and no self loops, which means no node has itself as a neighbor. Graph is connected and all nodes can be visited starting from the given node. Interesting. So what we're given as our adjacency list is this node, class node, which has a value, and then it has neighbors, which are also nodes, which presumably also have a value, and neighbors, and so on. So I think we can actually do is we could try to clone the graph just to generate some solutions. We could maybe clone the graph in we could potentially clone the graph. We could potentially clone the graph using at least one of the two graph traversal methods. We can either use a level order traversal or depth first search. But I think it's possible that we could clone this graph using a depth first search. We could clone with DFS, and I'm thinking the way we could go about this, right, is that since we have a connected graph, we also want to be wary of cycles. But when we're worrying about neighbors, I think we only necessarily have to worry about visiting the parent node more than once. This is just because of how recursive functions stack calls, right? If we were to view it like this, right, we could stack the calls like this, right? And if we visit 1, right, then we're going to visit our neighbor, which is 2, right? Then we want to visit our neighbor, right, which is going to be 3. We want to visit our neighbor, which is 4, right? And we'll still visit neighbors as we visit the remaining neighbors of all of these nodes. But I think what I'm trying to get at is that once we have access to the node in the recursive stack, or just the way that recursion orders code, we don't necessarily have to worry about revisiting them, since we can use a set basically. So we'll be able to use a set or a map to make sure that we don't revisit parent nodes. So what we want to make sure is we don't want to revisit parent nodes. Don't revisit parent nodes. And I think if we don't revisit parent nodes, we should be able to avoid revisiting or ending up in a cycle. So I think we could clone DFS. I think we're also going to need access to a map, because we're going to want to be able to insert nodes into whenever wherever we want. Actually, what do I mean when I say that? So if we're going to clone with the depth first search, presumably we'd start at index 1, right? And if it doesn't exist, right, we're going to add it, right, to our map. And so the map is basically our way. Map lets us keep track of nodes created. So we'd pretty much get any node based on a particular value. We know that all the values are unique, so we can access any node. So if we're in our DFS, we'll be like, hey, have we seen 1 before? Well, we haven't, right? So we're going to add it to our map and visit its neighbors 2 and 4. Right, well, if we do that, then we can visit 2. We haven't seen 2 before, right? But we've got to also remember that 4, right? We'll still end up visiting 4, right? Since we're visiting the neighbors of 1, 2, and 4. So we're still going to end up visiting 4, right? We're going to visit 2, right? Visit all the neighbors of 2, which would be 1 and 3. When we visit 1, we're going to say, hey, have we seen this number before? We have. Right, we haven't seen 3 before though, so we want to create it and add it to our map. Right, so I think we could probably jump into an implementation of this that we want to figure out. Maybe we could scaffold this a bit better, actually. So we're going to have a map, right? And this map is going to be a new map that maps numbers to nodes, basically. And this is actually going to be our cloned map, or the map that stores our cloned nodes, right? And we're going to have a DFS function, right, which is definitely going to start with a particular node. Right, we want to use the node's values as an ID, so we'll start with the node's value. Right, we'll pass in the map, and would we need anything else? We have the node's value in the map. We'll have the map to avoid cycles. It's also going to allow us to hold our cloned nodes. So let's run with that for now. Right, and just when we return, we're going to be able to return map.get, which would be the first value, right? The first cloned node, right? So the node they're passing into this function is the first node that they're giving us, right? And we want to return the first clone node, right, to return the clone graph. Now we can try and implement this DFS function, right? We're going to call this value, which is going to be a number. Now I'm seeing this is the other thing, right? We're also going to need Oh no, we should still be able to visit the neighbors. Okay, so we'll have map, which is going to be a map of number to node, right? We're not going to return anything. We're just going to modify map by reference, right? And we're going to have our map, right? We're going to say, hey, have we seen this value for a particular node yet, right? So we say if, so let's try and scaffold this, right? As if we were running this, right? If haven't seen value, right? What do we want to do? We're starting with 1, right? 1 is our node's value. And we actually, I see what's happening. So we don't want to pass in the value. We want access to its neighbor, so we're going to have to pass in the node. Right, we haven't seen, if haven't seen node.val before. Have we seen 1 before in our map? We definitely have not, right? So we want to create it in our clone map. So maybe a better name for this map would be clone map, right? Create clone for map. Add to map. So we haven't seen 1 before. Let's create the clone for 1, add it to the map. Right now we have to visit 2 and 4, right? So we want to visit our neighbors, right? So now we're going to visit 2, right? Well, have we seen 2 before? Well, we haven't, right? So you want to add it. You want to add it, right? And create it. But I think this is also the problem, right? Because we also want to, we cloned it, we created a clone for this node right here, right? If we create clone node for map, right? We also want to have it mimic its neighbors. So when we're visiting our neighbors, right? Maybe when we visit our neighbors, right? Maybe what we'd like to do so we want to visit our neighbors. We're visiting our neighbors because we can just visit node.neighbors for const node of neighbors. Now we're visiting them, we also want to propagate, right? Cloned node.neighbors is going to be an empty array. We want to get values into that, right? If we do the DFS, right? Let's say we did a DFS of 2, it's going to create a node for 2. Well, if we create the node for 2, right, the cloned one, we want to be able to add it to cloned node.neighbors. Now, how would we do that? Maybe we can do it I see. I think we just want to break up how we do this. So I think we're just going to want a set, right? We'll call it scene. It's going to be a set of numbers. And I think the goal with this value, this set, is going to be to allow us to differentiate between the nodes we visit and the nodes we create nodes for, right? Because I'm thinking if we visit our neighbors here, right, if they don't exist in clone map, create them, right? And then what we can do is just we can just cloned node.neighbors, right? So we'll have the neighbors for the clone node. We can just push the node, right? So if it doesn't exist, right, create them. Otherwise grab it from cloned map, right? We can just say cloned node.neighbors.push, right? And we can just push that cloned neighbor onto it as a neighbor, right? Right, and then we can just visit that neighbor, right? So we'll do, hey, does 1 exist? No, right? And we'll check if we've seen 1 before as a parent node. We haven't, so we add it. Then we want to say, hey, if it doesn't exist in clone map, create it, right? So we can push it onto the neighbors. And this is why we had to separate these scene set and cloned map, because we're going to be creating them sometimes, but we still want to be able to visit them even though it's been created. So we're going to push that node 2, then we're going to visit 2, right? But not the clone 2, the original 2, right? Which we can be able to visit because we're visiting our neighbors, right? And then we're going to say, hey, if we've seen 2 before, we haven't, we're going to add it to our map, right? And now we're going to see appear, right? Creating code for node, right? If node doesn't exist, right, then we're going to want to create a clone for the map, right, and then add it to the map. Otherwise, just grab it. We can just grab it from map, right? And then we want to visit. We're going to want to visit 1 and 3, right? So we're going to say, hey, right, visit our neighbors if they don't exist. Well, 1 already exists, so we can just grab it and push it onto 2's neighbors. 3 doesn't exist, so we're going to create it, right? Add it to the map, right? So it's going to become as 2's neighbor, and then we're going to visit it, right? And then we're going to say, hey, have we seen 3 before as a parent node or as its own vertice? No, right? So we're going to we haven't seen it before, but it actually already exists since we made it when we visited 3, meaning when we visited 2's neighbors 3. So we just really want to visit its neighbors. So this scene map really shows us, right, what nodes neighbors we've visited, right? And so I think when we visit 3, right, we're going to say, hey, visit 2, or we're going to push it onto its neighbor. We're going to visit, well, we've already actually seen it before, so we're actually not going to do anything with it. We're going to visit 4, create 4, right, push it on to 3's neighbors, and then visit 4, right? We've seen 1 before, so we're going to push 1 on to 4's neighbors, right, and visit 3. Well, we've already visited 3, so we're just going to push it on to its neighbors. And then we should be able to go all the way back to 1, and then we'll say, hey, does 4 exist? Yeah, it does exist, right? We'll grab it and push it onto our neighbors, and then we'll visit 4, but we've actually already seen it before. So there's a difference between seeing it and cloning it. And so I think that's kind of the secret key to this problem. So you can say if, right, we haven't seen, if we have not seen node.val yet, right, then we're going to want to do some work, right? And so we're going to see here, right, we're going to say is const cloned node. If we haven't seen this node before, right, we're going to want to clone it, right? Right, so we're going to say, does our cloned map, right, already have a node for this ID? And since it already has a node for this ID, what we're going to do is just do cloned map.get node.val. Otherwise, right, we're going to want to create a new node, right, with node.val as its value. Right, and we actually won't know if we just created or got it from the map, so we're gonna have to do a quick check, right, because we want to add it to the map. Right, we can say if cloned map, right, I'll make this slightly bigger. It's actually a little hard to read like this. If cloned map, right, does not have a node for node.val, right, but we know we just cloned it, right? So we're going to want to do cloned map.set, right, for this particular node value, right, the cloned node. So we added it to the map, right? Well, now we want to visit our neighbors, right? To visit our neighbors, we're going to want to do neighbors of the original. We're going to say const neighbor of node.neighbors. I think that's what it's called, neighbors. So we're going to want to visit those neighbors, right? But now I actually want to do the same thing we did up here, right? If it doesn't exist, right, then we're going to want to add it to the clone map. Otherwise, you want to grab it, right? So we can push this forward, and it's going to be a little bit hard to read. We'll say, right, the cloned, we'll call it cloned nay for cloned neighbor. And instead of calling it cloned node, we'll call it cloned nay, right? And what we want to do, right, is also we just cloned a node, right? Either if we cloned it or if we got it from the map, we want to push it onto its neighbors. So we'll say cloned node, right, dot neighbors dot push cloned neighbor, right? And then we can go even further with our depth first search, right, with this neighbor node, right, with the scene set, the clone map, right? And I think we should end up with something that makes sense. So let's see if this makes sense. We're going to do a map, create a new map to start. And we can actually just shove this into the code here. So just do one call, but we're going to start our DFS with 1, right? Have we seen 1 before? We've not. We haven't seen 1 before. Since we haven't seen 1 before, right? And we haven't seen 1 before, right? Oh, right. So now that I've noticed we haven't seen 1 before, right? We want to add it, right? We'll do scene.add node.val, right? After now you say we've seen it, right? Well, does it exist in clone map? Well, it doesn't, right? So we're actually going to create a new node with node.val, right? And clone map still doesn't have a node for this, so we're going to set node.val equal this is cloned node. So we cloned 1. Now I want to visit all the neighbors. So we have this one here, but 2, 3, and 4 are not here yet. Visiting the neighbors of 1. Now we're going to check for a cloned neighbor, right? So does our cloned map have a value for 2? It doesn't, so we're going to create a new node, right, with value 2, right? Set it in the cloned map. So now we have a cloned map with values 1 and 2 in it. We're going to push 2 as a neighbor of 1. Then we're going to visit the original of 2. Have we seen 2 before? We haven't, so let's add it. Then we're going to try and create a node for 2. Well, we're check, does the clone map have it? Well, it actually already has it, right? So let's just check the neighbors of 2. Well, we have a neighbor of 1. Well, does the clone map have 1? It does, right? So we're going to push 1, right, as a neighbor of 2, which is actually the cloned 1, which is perfect. So now we have this edge created here. Then we're going to visit the neighbor. Then we're going to visit 1, right? We've actually already seen 1, so we're not going to do anything. Then we're going to visit 3, right? Well, we actually haven't seen 3 before, so we're going to create it, add it to the cloned map, add it to scene, right? Then we're going to visit 3's neighbors. We're going to create it, right? And push it as a neighbor onto 2, and then visit 3. Well, we actually haven't seen 3 before, but we actually have already created a node for it. So now we're going to visit 3's neighbors. We're going to check if 2 exists in the clone map. It does. So we're going to get the value of 2, push it on as a neighbor of 3, then visit 2. We've already seen 2, so we're going to pop out of there. Visit 4. We haven't seen 4 before, so we're going to add it, create it, visit its neighbors, right? We're going to try and pull 1 down, but 1 already exists. So we're going to push it as a neighbor to 4. Try to visit 1. We've already seen it. Go back. We're going to visit 3, right? But before we visit 3, we have to check if it exists in the clone map. It already does. So we're going to push it as a node, as a neighbor of 4, the cloned neighbor of 4. Then visit 3. We've already visited it. So I think this makes sense. And we called this map. So I think we can just do map.getNodeVal. So we actually, it's like we bounced a lot between clone map and cloned map. Line 30. Use clone map. Then line 36. We'd like us to return null. I see. So we have the set and the map. We do map.get node.val. Interesting. So it seems like we're not actually copying it somehow. We're working with the original nodes, then visiting the neighbors of nodes. So we must return a copy of all the nodes in the original graph. So are we missing nodes? We were to print, right, we end up visiting the neighbor itself, then pushing cloned neighbor. We must return a copy of all the nodes in the graph. So maybe we're not copying every single node. Oh, I think I see what's happening. So when we create a new node here, we copy to the code above, but we're actually creating node.val. What we want to do is create a neighbor. We want to use a neighbor's value, right? And then when we say, right, when we check if the node exists in the clone map, it's actually with the main node's value. What we actually want to use is neighbor.val, which now I'm seeing is why all of this is messed up, right? And we're still doing get up here. All right, so it looks like that works for that first one. Nice, so it looks like this does work. And notice we have to be careful working with two nodes that are very similar with the block of function that we called. We're still referencing the old code instead of the, and I think a linter would have helped with this. You would have noticed this sooner, but what is the time complexity? I think the time complexity is, I wonder what m here. We said try to intuit the DFSO of n plus m version. This version, at most, right, we're visiting every node in the adjacency in this data structure based adjacency list. So I want to say it's linear time, but they're saying plus m. I wonder what the m is. I think I see that. But I think it actually it's n times m. Or I guess because for every node, we're visiting every node, and for every node, we're visiting all of its neighbors. We assume that every node has m neighbors, that we're going to do visit every node plus m, which would be the number of neighbors. So it'd be every node had 2 neighbors. If we had 4 vertices and every node had 2 neighbors, n plus n would be 6 total iterations. What I'm trying to get at is that if we had 4 neighbors with 4 vertices with 2 nodes for every vertex, we actually have 8 operations. So I'm thinking n times m would be the same for space as well, since we're going deeper into the DFS. I don't think this is n plus m. Number of edges. Oh, right. I think I see what they're getting at. Because you only visit with the scene array, we only visit it once. So I was assuming that even if you go into the recursive function and then you instantly exit with 15, line 15 here, it's still n by m. But I guess what they're saying is m by m, since we perform, this is essentially a no op, since it doesn't since we've already seen the node. In that sense, we are visiting every vertex, but it also has to do with the, I think I see what they're saying, the number of edges, because we're going to, oh, there we go. Why is it O of n plus n instead of O of n times n? I think this is actually semantic. I think this is the same thing, because the number of edges, I was counting it as if there's only 4 edges, but since it's undirected, you could say that node 4 here, the number of edges between 1, 2, and 4 is actually 4, even though there's only 2 edges you can see, because there's an edge, right, going from 4 to 1 and 1 to 4, which technically is an edge, and there's edge going from 1 to 2 and 2 to 1, which is 2. So the number of operations is still 4 times 2, which is 8. It's just m is the total number of edges in totality, where I was using a constant before. I think I see what they're getting at here. I think that's a wrap for day 49.